Hello and welcome to this lecture. This lecture is on variance. Okay, so we've seen expected value of a random variable before. Variance is a special type of an expected value. It's related to a special type of calculation involving expected values. Okay, so we'll see the motivation for variance and why it's needed and its definition. Once again, this is something you've seen before in Stats 1. So the presentation will be quick and we'll focus on only the new things mostly that we are doing here. Okay, so here's the motivation. Okay, so if you remember, I started motivating expected value, saying that instead of giving the whole distribution and the entire data, you can give the average value. It sort of represents the distribution in some sense. Okay, so here's an example. Okay, so to assess how good is the expected value, here are three distributions. First, I start with an x which is actually a constant. Okay, x is equal to 10 with probability 1. Okay, that's a constant. And there's a random variable y which is going to take 9 with probability half and 11 with probability half. And there's yet another random variable z which is going to take value 0 with probability half and value 20 with probability half. Now interestingly, if you actually summarize and find expected value for each of these random variables, you will get the same answer. The expected value of x is 10, expected value of y is 10, expected value of z is 10. Okay. But clearly, the three random variables are very different, isn't it? The x is constant, y, okay, at least you can say it's close enough to 10, 9 and 11. Z looks quite a bit far away, right? 0 and 20. So just by giving the expectation alone, you really cannot distinguish between these kind of random variables. It doesn't seem like you get a sense of what the random variable is with just the expectation, okay, the expected value. So you need something more, and that something more is usually should measure some sort of a spread, isn't it? So you can see here that while the expected value correctly gives you the center of the random variable, it appears that the spread is also important and you need some other way to indicate spread. Okay, so that's where variance comes in. Once again, you've seen this before. I'm just motivating very quickly with a simple example. Okay, so here's the definition for what is called variance and a very closely associated term called standard deviation. Okay, so if you have a random variable x, we'll denote the variance by this VAR of x. That will be our notation for variance. It's simply defined as the expected value of this function. Okay, so notice, so this guy is some function of x, isn't it? So variance of a random variable x is the expected value of a specific type of function of x. What is that function? X minus e of x whole squared. So some people get confused with this e of x usage. What is this e of x? E of x, remember, is some constant, isn't it? Think of e of x as some constant. Okay, so you have a random variable x and somebody tells you what its expected value is. Okay, so e of x, as far as I'm concerned, is a number, right? It could be 10 like in the previous case. Okay, and then I have a function x minus e of x squared, right? This is just a function of x, okay, which is another random variable, and I have to take the expected value of that. Okay, so we'll see some illustrations on how to compute, but this is what the definition is. Okay, hopefully the definition is clear. Okay, so the variance involves a squaring of x, right, in some sense. So if x has some units, it makes sense that the square root of the variance will also have some meaning, and that is where the standard deviation comes from. Okay, so standard deviation is simply the positive square root of the variance. Okay, so now like I said, variance is simply the expected value of another random variable, which is a function of x given by x minus e of x whole squared. Okay, so one way to write out this formula, since we know it's a function of another random variable, is to sum over all values in the range of x, okay, t in range of x, t minus e of x whole squared times probability that x equals t. It seems like I'm using simply the formula for expected value of a function of a random variable. I know that's true. Okay, now variance is non-negative. Why? Because this takes only non-negative values, right? X minus e of x, what is inside the bracket could be positive or negative, but once you square it, it's going to go positive. So this clearly, the summation is going to be non-negative. So standard deviation is well defined. It will be a real number. You don't have to do square root of negative numbers. You'll get square root of only positive numbers or non-negative numbers. Okay, so the units of the standard deviation become the same as the units of x. If x has some units, the variance will become square of that units, and standard deviation will go back to that original unit. Okay, So you can see where this x minus e of x comes from, right? So if you have a lot of values in the range t which are far away from e of x, then the variance is going to be larger and larger. Okay, so something that is far away on the left side can be compensated by something that's far away on the right side, right? So the expected value will continue to remain in the middle, but when you do the variance, whether it is on the left or right, it's going to only have a positive contribution, right? X minus e of x whole square, x minus e of x whole square, so it's going to have a positive contribution. So the spread is going to be sort of well captured by the variance in some sense. Okay, it's only one number, but still it captures the spread very nicely. So this is the basic motivation for the definition. Let's go back to our example where we had these three random variables which have the same expected value, but their variances and standard deviations are different. You can do this calculation very easily. Variance of x is, you have to sum over all values in the range of x, which is just 10. So it's 10 minus 10. Where did I get this other 10 from? This is expected value of x, right? This is t from range of x, right? There's only one value. So you get 0, the variance is 0, standard deviation is 0. So variance is 0 means the random variable is a constant. Okay, so anytime random variable is a constant, variance will be 0. Anytime variance is 0, random variable is a constant. Both of those are true. Okay, so let's look at variance of y. Once again, 10 is the expected value of y. Okay, so you do every value from the range. So you say take 9 minus 10 whole square times probability that y equals 9. That's 1 by 2, right? So once again, if you want me to write it, this is t that belongs to the range of y. This is expected value of y. This is probability that y equals t, right? So that's what you do. You do repeatedly, add it up. In this case, you get 1. Okay, so the variance now becomes 1. So even though expected value of x is equal to expected value of y, the variance of x is 0. The spread indicator is saying 0. It's not spread out at all. It's concentrated on one value. On the other hand, variance of y ends up being 1 and the standard deviation is 1. Okay, if you go ahead and compute variance of z, you get 100 and the standard deviation is 10. Okay, so you see how these three random variables at least, which have the same expected value, by computing the variance, we are able to summarize it very nicely. It sort of indicates that z has a larger spread and x is a constant and y is sort of reasonably closely spread from the center. Okay, so easy example. Okay, so let's do to a slightly more complicated example where we're throwing a die. So your x is a uniform distribution from 1 to 6, right? 1, 2, 3, 4, 5, 6. Expected value of x is 3.5. We've done this calculation before. So if you do variance, you'll see you will get 1 minus 3.5 square times 1 by 6, 2 minus 3.5, 3 minus 3.5, 4 minus 3.5, 5 minus 3.5, 6 minus 3.5, 1 by 6, you will get 35 by 12, which is 2.916. Okay, so the standard deviation is the square root of 35 by 12, and that will end up being, so this is basically square root of 35 by 12, and that ends up being 1.7078. You see the calculation, right? So this calculation is hopefully really easy. I'm going to make this statement. So if you're given a PMF of x and that x has a very small range, okay, the range is not very big, it's not infinite like geometric, you're not going to get some nasty summations which you don't know what to deal with, all that, then its variance and standard deviation can be quite easily computed. Okay, so that's great. So we had this meaning that expected values like the average value when you repeatedly see random variables. Where does variance come in? Or how do you see variance? Variance is also an expected value. So if you compute the expected x minus e of x whole squared, you're going to get something close to the variance. So we'll see some simulations of this on Python soon enough. Okay, so that's throwing a die. So once again, given the PMF and the range is small, it's easy to do the summation. Variance and standard deviation can be quite readily computed. Okay, so let's go to properties. Okay, so the properties are quite easy to establish. I think I'm not doing too many proofs for the properties. Okay, so let's look at the properties. So if you remember, for expected value, we saw the linearity of expectation played a huge role. Expected value of ax plus by became a times expected value of x plus b times expected value of y. Okay, so in this case, things are slightly different because you have the squaring going on. So anytime you have a squaring going on, things will not be linear. Okay, so things will change a little bit. So for instance, I'm scaling x by a. Okay, so I'm multiplying it by a. If it were linear, you would only get a scaling by a. but in this case variance is sort of squaring, there is a squaring involved. So when you scale x by a, the variance of ax gets squared by a squared. Okay. So this is not very difficult to establish. I am not going to write down lengthy proofs of this, but it is important to remember, and it is easy to sort of see where it will come from, right. So you just take expected value of x minus e of x. Instead of x you put ax, right, and then the a will come out, but then there is a square, so you will get a squared, and the a squared will come out of the outer expectation, you will get a squared times that. So it's a very easy thing to establish. So when you multiply a random variable x by a, the variance gets amplified by a squared. Okay. So when you take standard deviation, I'm going to take the square root, but remember it's a positive square root, so it's going to be standard deviation of x multiplied by absolute value of a. So even if you were to multiply x by a negative number, the standard deviation gets only multiplied by the absolute value, something to remember. Okay. The next thing we saw very interestingly towards the end of that expected value class is translating a random variable, right. So if you take a random variable x and then move it around, then we saw the expected value also moves around like that, right. So the random variable has some distribution, you move it around, the distribution will also move around. Okay. But notice what happens to the variance. If you move the random variable, like translate it, the variance is not going to change, the spread about the center is not going to change, and that behavior is reflected in the third property here. Okay. Variance of x plus a is equal to variance of x. Okay. So this again, these are easy things to establish. Maybe I'll just write down a proof for this alone. Okay. See, this you want to write variance of x plus a, right. So it's going to be x plus a minus expected value of x plus a, the whole squared, right. This is going to be expected value of x plus a. Remember, this expected value is linear, isn't it? So this will go minus expected value of x minus expected value of a, but a is a constant, so you'll just get a. So this a and a will cancel, and that becomes variance of a. So it's very easy to prove these kind of statements. The proof itself is not so complicated. You just write down the whole thing, you'll get it. But the property, understanding the meaning of this property. So why is the spread not affected? When you multiply by a, the spread is going to be increased, right? So if, imagine a being a greater than one number, right? So if a is 10 or something, if you had a spread, when you multiply by 10, it's sort of getting spread out more. So the variance amplifies by a squared, standard deviation multiplies by absolute value of a. Okay. On the other hand, if you were to shrink the random variable, let's say you multiply by 0.5 or 0.1 or something, you expect the variance to decrease, and a squared is how it decreases. On the other hand, if you don't scale up or scale down, you're just shifting the random variable, you don't expect the spread about the center to change. So that's also reflected in this property. So there's a simple meaning for these properties, while the proof is also not too complicated. Okay, so scaling and translation is easy to establish. Okay, so I want you to contrast with similar properties for expected value of x. I mentioned that, and you can see it's different because expected value of x is sort of linear. Here you have that squaring term, so it becomes a bit different. Okay. All right, so there's another formula for variance. The formula we saw so far is expected value of x minus ex whole squared. It turns out you can do some simplification there, and in fact the variance of x is equal to expected value of x squared minus the expected value of x, the whole thing squared. Okay, so notice this difference here. Hopefully you can see this difference. Here you have expected value of x x squared. Okay, so the x square is inside. Okay, so here you have expected value of x, that whole thing squared. Okay, so notice the slight difference here. It's not the same. Okay, so notice. I mean, sometimes if you just glance at it, you won't see the difference. The 2 has sort of gone out of the bracket. So you do expected value of x first and then you square. Okay, so if you want me to write it down clearly, see expected value of x squared is summation over t in the range of x, t squared probability of x equals t. What is expected value of x the whole squared? It's summation t equals tx, t times probability of x equals t, this whole thing squared. Okay, so both of these will not be the same. Okay, so this is different, this is different. There will be a lot of cross terms here when you do this. There will be no cross terms. This is t squared. So these two are not the same. Okay, so don't think that these are the same. Okay, so the proof is here. I don't want to go through the details of the proof in this class. You can see it relies on the linearity of expectation and the fact that expected value of x is a constant. You can write down the proof. Okay. So there's another term I want you to remember. Expected value of x is called the first moment. Okay. This is called the first moment. Expected value of x square is called the second moment. Variance of x is called the second central moment. Okay. So this word moment you will see quite often being used for these kind of functions. You can imagine expected value of x cubed is called the third moment and all that. Okay. So these moments are interesting, and basically what we are trying to see here, hopefully you can see the picture here, the moments are actually the things that summarize your random variable, right? Expected value of x is the first moment. It gave you a good summary which is connected to the average value. The expected value of x squared gives you the variance, not directly, but expected value of x squared minus expected value of x the whole square gives you the variance, which is the spread of the random variable. Okay, what about third moment, fourth moment, you may ask, but usually first and second moment are very crucial, and that's usually good in a wide variety of applications. Okay, so that's alternative formula is very important. It's quite easy to use this alternate formula. You'll see in some examples it's easy. Okay, so one other property which is very useful is this sum and product of independent random variables. Okay, so we know expected value is linear. Okay, so for any two random variables x and y, whether it's independent or not independent, whatever, expected value of x plus y is expected value of x plus expected value of y, and this we used so interestingly in complicated problems to simplify our calculations. Okay, now in addition, if you know x and y are independent random variables, then you can say more. There are more very interesting relationships if x and y are independent random variables. Okay, so it's important to know that if they are not independent, you generally can't say anything more. But if they are independent, you can say something more. For instance, expected value of x times y becomes expected value of x times expected value of y if x and y are independent. Okay, only if they are independent. Otherwise, this statement is not true. Okay, it's important. And similarly, variance of x plus y becomes variance of x plus variance of y if x and y are independent random variables. Amazing, isn't it? So x and y being independent is a very strong and powerful sort of condition. It makes products, expected value of xy becomes expected value of x times expected value of y. Variance of x plus y becomes variance of x plus variance of y. So very powerful results. We'll see a quick proof of it. I just want to go through this in very quick detail just to show you why the independence is crucial, how it enters the proof and how you can't do it without that. I'll do it only for the first one. I'll leave the variance part as an exercise. Okay, so we know that this guy is summation over T1 in Tx, T2 in Ty, right? T1 T2 times probability that x equals T1 comma y equals T2. Now notice, since x and y are independent, this guy becomes equal to probability that x equals T1 times probability that y equals T2. This is a crucial simplification. So you will get something like this. So you can sum over all values. So this is another way to write these double summations. Write it as two summations, T1, T2, probability of x equals T1 times probability of y equals T2. It's the same thing. So I'm going to keep T1 fixed, okay, and then vary T2 alone, okay, and then do T1, T2, probability of x equals T1, probability of y equals T2. And then the next value of T1 comes, then you vary T2. So this is the same thing as doing T1, T2. This double summation can be written out in this fashion. Now what's nice about this inner summation is over T2. So T1 is constant, right? So these two you can move outside of the summation. So if you do that, you will get summation T1 belonging to Tx. So notice this little trick here, it's important. T1 times probability of x equals T1, and then you have a summation here inside T2 probability of y equals T2. What is this guy? What is this summation? Summation T2 in Ty, T2 times probability of y equals T2. This is expected value of y, right, which is a constant, right? So this expected value of y is a constant, and that guy will actually come out of this summation. Okay, so you get expected value of y times, what is this guy, summation t1 equals tx, t1 probability of x equals t1. What is this guy? This guy is expected value of x. So this whole thing becomes expected value of x times expected value of y. Notice how this factoring is crucial. If this factoring did not happen, right, if x and y were not independent, you are not going to get this, okay, at least not in this form. It turns out even if x and y are not independent, something like this can happen in some situations, but if they are independent, it's definitely going to happen. It's very easy to sort of establish the result in this fashion. Without this factoring, I wouldn't have been able to write it so easily, right? But you know, who knows, maybe something else will happen, but you can easily produce two random variables x and y which are dependent, and these two will not be true. Okay, so remember, this is not always true, this is important to remember. There can be x and y which are not independent, where some other factoring happens, some other crazy thing happens, and you come back to this, but this is not always true if x and y are dependent. Okay, so there can be dependent cases where this will not be true. Okay, so it's a quick proof. I just wanted to write down one proof as part of every week. You should see at least one proof which is easy to write down, but we'll stop here. We won't do any more proofs as part of this course. The second thing is an exercise. I will let you prove it. This proof is an exercise here. Okay, so it's a bit involved, but it uses this result. This result is useful here. Okay, so you write variance of x plus y using that usual formula, expected value of x plus y minus expected value of x minus expected value of y whole square, and then you will have a bunch of cross terms, right? So you square it, you will get a bunch of cross terms. You use expected value of x y is expected value of x times expected value of y, and you will magically get this final answer. Okay, so I'll leave it as an exercise. Some of these proofs you have to do and enjoy. Okay, so I'll let you do it on your own. Okay, so these are important. We're seeing very powerful properties for variance. Okay, so let's try and use the property to compute the variance of sum of two dice. So variance of one die we saw already. It is square root of 35 by 12. It was easy enough to compute. Now what about variance of the sum of two die, right? So let's say x is the first die, and then y is the number shown on the second die. X and y are independent. Okay, so this is the crucial assumption here. Okay, so it's not stated in the problem. It's what is the sum of two dice. I'll assume independent. It's usually not stated very clearly. Quite often people just assume this independence, but in this two dice case, you know, when you throw two dice, the two things are independent. So maybe it's not a reasonable thing not to state, but it's good to state it very clearly. So you want the variance of x plus y. So this, since they are independent, this is just variance of x plus variance of y, and you can quickly compute this as 2 times square root of 35 by 12. This can go out if you like, so this is square root of 35 by 3. Okay. So this was easy enough to compute, but notice if this independence was not there, right, then notice how difficult it would be to compute variance of x plus y, right? So you have to go through that whole formula, and then it's a bit more messy than you can imagine. Okay, so if you can compute, if you're given independence, it's a very easy calculation to do. Okay, so previously when we discussed expectation, we looked at expected value of common distributions. This was a pretty big and important thing that I did. I went through a lot of summations and complicated stuff. I'm not going to do that for variance. I'll just show you maybe 1 or 2 examples, very easy examples where I know I can quickly compute, but the other examples I'm going to leave as exercise to you. Go ahead and compute, but here is a table. This is a standard table. I would suggest just mug this up. I mean, just know this by heart. It's good to know them. Most people who work in statistics and probability would know, or at least know where to look. You can go to Wikipedia pages. They'll give you details of what the expected values, variances, etc. Okay, so Bernoulli random variable, expected value is p, variance is p times 1 minus p. the binomial random variable. It is binomials, it's not binomials, it's binomial. Okay, so it's this is not there. NP, we know expected value is n times p, variance is np times 1 minus p. Okay, so notice how it seems very close enough, it's very interesting, np times 1 minus p. Geometric p is 1 by p, and then the variance is 1 minus p divided by p squared. Look at Poisson, it's very interesting, expected value is lambda, variance is also lambda. Okay, and then if you take the uniform distribution from 1 to n, expected value is n plus 1 by 2, it's easy to see, and variance is n squared minus 1 by 12. Okay, so that's what it is. Okay, so let's do simple things. So let's say x is Bernoulli. Okay, so x is 0, 1, and this is p, and this is 1 minus p. Okay, we know expected value of x is p. The best way to do these kind of things is to find expected value of x squared. Okay, so expected value of x squared is 1 times p, isn't it? It's also p. Okay, so in fact any expected value x bar 3, x bar 4, whatever you do, you'll get 1 into pp. Okay, so now variance of x is expected value of x squared minus expected value of x whole squared. So you get p minus p squared, it's p times 1 minus p. Okay, so Bernoulli is easy to do. This is the first case. Right, so notice how this alternate formula is very nice. You know, expected value of x squared is very easy. So now for the second one, binomial NP, it's I mean if you start calculating, so notice what will happen. Yes, so supposing x is binomial NP, this expected value of x we know is NP. We found it by two methods, right? One was we wrote the summation, complicated summation, and we simplified it, we got NP. The other was this wonderful trick we had where we said x is actually x1 plus so on till xn, where xi are IID Bernoulli p. So this is very, very important. This independent assumption is very, very important. So we got a very simple way to compute this, right? So just linearity of expectation, take expectation on both sides. Okay, so this is something that people typically do. You just take expected value of x is equal to expected value of x1 plus xn. Now use linearity, it says n times expected value of each of these guys, and that's p. Okay, so easy to get. Now we know we can use it for variance also, right? Why? Because this is IID, right? Independent. So that implies variance of x is simply variance of x1 plus dot 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 variance of xn. Okay, so that's n times p times 1 minus p. So each of these guys is just Bernoulli, so that's p into 1 minus p, so np into 1 minus p. Look at how easy it was. Okay, otherwise if you want to compute directly, expected value of x squared will be summation k equals 0 to n k squared, and choose k, p power k, 1 minus p power n minus k, right? This ends up being a slightly more complicated summation. In fact, once you know the variance, right, you know that this is variance plus the mean squared. Okay, so you know you can find expected value of x squared easily using this trick. I mean, otherwise if you have to directly compute the summation, seems like this is a slightly more involved summation to calculate. Okay, but how did I find this? This is variance plus this is expected value of x whole squared, right? So variance of x is expected value of x squared minus expected value of x whole squared. So you can sort of use it in reverse and get these complicated type of summations easily figured out if you know the variance. Okay, this is a sort of trick you can use to do it. This is how you compute for complicated distributions. I'm not going to go into detail of the other calculations. I'll leave it as an exercise for geometric, Poisson, and uniform. You can do those summations with all the few methods that I gave you for finding the summation. You can do variance of common distributions this fashion. Okay, so I have some working here. I'll skip this. Okay, so we saw in the expected value that by translating you can make the expected value of a random variable 0. Okay, now here is something that you can do a little bit more. You can say a random variable is standardized if the expected value is 0 and the variance is 1. Okay, so this is sort of like standardizing the random. If you have a random variable, it's not at 0, it's not around 0, it is somewhere else translated. You move it, you can make it 0. Now what about the variance? The spread may be a lot. Can we standardize the variance? It turns out making the variance 1 is some sort of a standardization. And here is this wonderful theorem. Okay, if you have any random variable x, okay, it should have some expected value, standard deviation, etc. And then x minus e of x divided by sd of x is a standardized random variable. Okay, you can try and prove this. It's not very hard. Supposing you say y is, this is y, you can show expected value of y. Okay, this 1 by sd of x will come out. Okay, this is just a constant, times expected value of x minus expected value of x, and that will go to 0, isn't it? What about variance? Variance of y, remember this is x by sd of x minus a constant, expected value of x by sd of x. This is the same as variance of x by sd of x. Okay, and this is like 1 by a, isn't it? This is like a constant here. So you will get variance of x by standard deviation of x whole squared, and that is just 1. So it's easy proofs, nothing majorly going on, but it sort of gives you something very important. This will come back to us and we'll use this in some interesting ways. So given any random variable x, so supposing you have a bunch of data, a lot of values, and maybe its mean is somewhere else, its variance is something else, and you want to be able to use it along with other random variables which have some standardized sort of properties. So one of the most useful things you can do is standardize it, right? So you just look at x minus e of x by sd of x. Okay, so hopefully you see that the PMF of distribution of x, okay, so PMF of y, okay, I'm sorry, PMF of y is very similar to PMF of x. Okay, so let me just put very similar in quotes. I'm not defining it properly. I'm just saying why, because y is just a translated and scaled version, right? So the shape of the PMF is not going to change. If it has a certain shape, it will probably get scaled, it will probably get moved around, but the shape and the general relative behavior is the same. So PMF is sort of, you can go from one to the other, okay, but the expected value is 0 and the variance is 1. So these kind of things are said to be standardized random variables. Okay, so so this sort of covers most of what I wanted to say about variance. Once again, it's a revision. You've seen this before, so I'm going through it very quickly. Okay, hopefully you got an idea of what variance is, what's the kind of notation we'll do, and what are the various ideas that one can use in manipulating these things. I'll leave you with one slide which is strictly additional material. I'm not saying that this is part of the course, but something you should know about existence of expected value and variance. Okay, so it turns out one can come up with a random variable for which expected value of x, the random variable x, for which expected value of x will go to infinity. Okay, what do we mean by infinity? The range has got so many values and the probabilities are spread so that when you multiply the value in the range by the probability and add it all up, you will get something that blows up. Okay, so it will keep on increasing. Okay, so here's an example, a very, very simple example. Half, just a random variable takes values 1, 2, 4, 8, 16, so on, powers of 2, and the probability with which it takes it is half, 1 by 4, 1 by 8, etc. Okay, so you can compute expected value of x, and you will see it will be half plus half plus half plus half, right? Every product is a half, and half, it will go on and on and on forever. So half plus half infinite number of times is infinity, right? So it blows up for you. So expected value of x blows up. So when expected value of x itself blows up, it turns out expected value of x squared will also blow up. So when there are two things that are blowing up in different ways and you start subtracting and all that, it doesn't make sense. Okay, so variance of x is not very well defined in this case. So these kind of situations can happen with random variables, but these are exceedingly rare. In most practical cases, you won't meet these kind of random variables, but somewhere in the corner of your mind, just remember, for theoretical purposes, anytime you use expected value of x, variance of x, you are assuming that they exist. Okay, so far I just wrote down everything. I never made a statement saying assuming this exists, but if you see a proper book in probability and statistics, they'll always say let x be a random variable with expected value and variance. Okay, so they'll assume it exists, assumes it's finite, for example, and then only they will proceed and give results. So all the results I stated using expected value, for instance, I said x and y are independent, variance of x plus y equals variance of x plus variance of course, all that holds only when they exist. Okay, when they don't exist, none of them hold. Okay, so I never kept saying that, but this slide is sort of like a, sort of a exceptional situation, and we're going to say, we know that these situations exist, but we live in the comfortable world where everything exists. Okay, so there are more examples I've given you. In fact, there are even more confusing random variables where even expected value of x is not well defined, as in you will not get anything. It will not be properly going to one value. At least in the previous case, it was properly blowing up, right? So here it won't even properly blow up. At one point it will say I'm positive, the next point it will say I'm negative. You can make it do a lot of other things, and it's not a proper well-defined sort of thing. Okay, so when it's not well defined, again expected value of x squared will go off to infinity, or something else will happen. So variance becomes ill-defined. So these kind of things can happen. In fact, I'm pointing out one more situation in the third bullet. You can have expected value of x being finite, but expected value of x squared can go to infinity. So basically, if you have x belonging to, so this is a standard example like this, and probability of x equals k, I'll say is proportional to 1 by k power 3. Okay, I've said proportional to because you have to divide by the sum to make it have adding up to 1, etc. So this is a standard example for the case where expected value of x will be finite, but expected value of x squared will go to infinity. So variance will go to infinity. So these kind of situations can happen. Like I said, the last bullet is where we are going to live as far as this course is concerned. In fact, entire program is concerned. Mostly we'll be living in this world, very comfortable world, where we're looking at well-behaved random variables, finite mean and variance. Okay. So once again, this slide is just sort of out of syllabus. I'm just putting it out there to tell you that these things exist, and we will be loosely aware of them, but we won't study these kind of situations very closely. Okay, so that's the end of this lecture. Thank you very much.